All right, guys, we are now moving on to Chapter 5, Heat and States of Matter. Remember, we are skipping Chapter 4, and we will come back to that in the spring. Our first section is on really what is this thermal energy, what is temperature, getting those basics in, talking about specific heat. So we need to talk first about the kinetic theory of matter. Remember what a theory is. A theory is something that explains what's going on within the thing. It's an explanation why. Okay, theories can change as we learn more about an object. So this theory could potentially change in the future as we learn more about what's going on at the atomic level. As you know, objects around us are always warming and cooling. Something's going on with their temperature. And the temperature of an object is related to what is going on inside that object. What are the particles? What are the atoms inside that object is doing? And the motion of those particles, how they're acting, how they're behaving, is what is described as the kinetic theory of matter. So according to the kinetic theory, by definition, matter is composed of particles that are atoms, molecules, or ions. Okay, those are some chemistry terms that are always in random motion. Keyword there is this random portion. They are moving. We can't predict where they are going to go. Because of this, the particles have kinetic energy that can be moved from one particle to the next. Particles are able to collide because they're all moving randomly, and when that collision happens, remember law of conservation of momentum, momentum can change. Energy can be transferred from one particle to another. So temperature. Okay, what is temperature? If I asked you what the temperature was in the classroom, you might say 71, 72, 68. Okay, what are we actually talking about? Okay, what we're really talking about is what's going on within those particles. The particles in that object, the air particles in our classroom, are moving at various speeds and have different amounts of kinetic energy. So when we talk about the temperature of a substance, we're actually talking about the average, okay, the average kinetic energy of all the particles. So if we had all sorts of little particles. We've got 5 particles here. And this one is 5, and this one's 4, and this one's 3, and let's say 6 and 7. And that's the measure of the energy inside of them. Each of these particles has a different amount of energy. Well, if we add up 5 plus 4 plus 3 plus 6 plus 7, divide it by 5, we are going to get an average of 5. So we would say here, if these are all the temperatures, that the average temperature, that average kinetic energy, the temperature is 5. As the average speed within the particles increases, the temperature increases. As things move faster, they heat up essentially, and that temperature then rises. But remember, temperature is the average. So you can still have cold spots, you can still have hot spots, but temperature deals with that average. Quick review of temperature scales. This should be a review. The SI unit is kelvins. However, most commonly in science, we talk about the Celsius scale, and here in the United States, we use the Fahrenheit scale for all of our temperatures. Again, just the conversions, okay, 273. So to go to Kelvin to Celsius, subtract 273. To go from Celsius to Kelvin, you add 273. Okay, you cannot have a negative Kelvin number. That is because of this idea called absolute zero. Okay, and that is where all particle motion stops. So if we can get all the way down to 0, that random motion of the particle stops because it's gotten so cold, so it slows down more and more and more, and eventually it stops. Okay, back to this idea of kinetic energy as we talk about what is thermal energy. Okay, those molecules are in random motion. So the sum of all the energies that an object has is its thermal energy. Okay, kinetic energy, energy in movement. Okay, kinesiology, study of movement. Potential energy, what could it possibly do? You have potential to earn a certain grade in this class. It doesn't mean that you're going to get there because all sorts of things have to happen for you to do that, but you have that potential. So thermal energy is that sum of all the energies in an object, not only what it's actually doing, but what is it capable of doing. Things that thermal energy depends on: the temperature, how much of the object you have, and the type of substance. Okay, and this is all going to lead us into the formula that you guys did on the pre-reading: Q equals MC delta T. Okay, all of these components are right here in this slide: thermal energy, temperature, mass, and then that type of substance. That's our specific heat, but we'll get there in a couple of minutes. So heat. Can you tell if someone sat in your chair before? I think you would all answer yes. Why is that? It's because thermal energy flows. Remember that random motion. Even if two objects are touching each other, a person and the chair, that energy flows between the two objects. So heat is thermal energy that is flowed from higher temperature to lower temperature. Here's the key: high temperature to low temperature. So if we have hot, that thermal energy, let's go ahead and go blue here for cold. Okay, so heat gets transferred. So when you think of right now out in the winter time, if I walk outside, am I warming the air or is the air cooling me? Okay. So heat is a form of energy. Energy is measured in a unit called joules. We abbreviate it capital J. It is named after someone. This is a unit that you need to know. So when we're talking about thermal energy, okay, we're talking joules. Reminder again, you see it more than one time, it's probably pretty important. Thermal energy always flows from the warmer object to the cooler object. So think about this one. Where does heat flow when making ice cream? The ice cream cold, air hot, flows from hot to cold, so air to ice cream. What about here? Where does it flow when the ice cream melts? Okay. Ice cream cold, air hot, so it goes air to ice cream. Let me back up. I forgot the first one was making ice cream. Now when it melts, when we're making ice cream, it goes from the cream mixture to the ice. So my bad on that first one. It goes from the ice cream mixture, which is the warm, to the cold ice mixture. Okay, measuring specific heat. You use a device called a calorimeter. Okay, we will use a calorimeter in lab tomorrow. We're going to use 2 styrofoam cups. They can get to be coffee cans and smaller coffee can, or like a vegetable can, all the way to very scientifically precise measurements that would be used in a food science laboratory. So, specific heat. Okay, this is a big topic. It can be hard. So as you are listening and taking notes, if you have questions, please raise your hand so that I can come help you through this concept. Okay, so you've walked on a beach in the summer, whether it's a beach here in town or by the ocean. The sand feels a lot warmer than the water. Okay, why is that? They're two different substances, but they're both receiving the same amount of energy from the sun. The sun doesn't discriminate. It heats the sand with the same amount of energy that it gives the water. But because they are different objects, different substances, they absorb that heat, and the temperature change, the response to that heat is different. And this is what specific heat is. Okay, it's how quickly the temperature is going to change depending on how much thermal energy is going. So we have to keep some stuff constant here. So equal mass. Okay. If I have 1 kilogram of water and 1 kilogram of sand, the water is going to take 6 times as much thermal energy to raise that temperature 1 degree Celsius. So if I put 12 units of thermal energy in, 12 joules, okay, it's going to take a lot more, 12 times 6, 72 joules for the water. 12 for the sand, 72 for the water to both be changed 1 degree Celsius. Specific heat is exactly that number. We know these numbers for all sorts of substances. So specific heat is the amount of thermal energy, okay, thermal energy is in joules, needed to raise temperature, degrees Celsius, okay, mass, kilograms. Okay, we're always going to deal with 1 kilogram, 1 degree Celsius, because it gives us a constant. So specific heat is joules per kilogram degrees Celsius. That is the unit. It is a derived unit again. It is a crazy unit, so make sure you take some time to memorize it. That also means that when you're putting things into the formula that we're going to get to here in a minute, you've got to make sure you're dealing with kilograms. You've got to make sure you are dealing with Celsius. Okay, so there it is, joules per kilogram degrees Celsius. Many different objects have different specific heats. The only object you need to have memorized what its specific heat is water, 4,184 joules per kilogram degrees Celsius. If it's anything else besides water, we will give it to you. But make sure you know that water's specific heat is 4,184 joules per kilogram degrees Celsius. So if thermal energy can flow, that means that an object can have a change in thermal energy. Thermal energy of an object changes when that temperature changed. So we get kind of a crazy formula. Q is the change in thermal energy. C, specific heat. You've got mass for M and T for temperature. So you get this formula. Change in thermal energy equals mass times the change in temperature times the specific heat. Q equals M, TF minus TI times C. TF minus TI you will also see as delta T, change in temperature. Okay, so I might just say the change in temperature was 5 degrees Celsius, or I might say the initial temperature was 25 degrees Celsius, the final temperature was 30 degrees Celsius. It's saying the same thing. So let's do a practice problem here. Find the change in thermal energy of a 20 kilogram wooden chair that warms from 15 degrees Celsius to 25 degrees Celsius if the specific heat of wood is 1,700 joules per kilogram degrees Celsius. Take some time, identify your variables. Okay, remember the formula. Remember delta T, TF minus TI, and see what you get. Okay, try this one. The air in the living room has a mass of 72 kilograms and a specific heat of 1,010 joules per kilogram degrees Celsius. What is the change of thermal energy when the air cools from 25 degrees Celsius to 20 degrees Celsius? Okay, think about it here. It's losing temperature. So should the change in thermal energy be a positive or a negative? Okay, go ahead and calculate that and make sure you are set to go. If you have any questions, guys, on these problems, please let me know. This is the last formula that we are going to be working on this semester, but it is important that you know it. It is going to come back in a few other classes that you take throughout your high school career. So let's make sure we get a good, solid understanding of it now. If you have any questions, again, come talk to us. That's what we're here for. Make sure you are ready for lab tomorrow. Lab entry ticket is posted in Skyward. Make sure your lab notebook is set up and be ready to go tomorrow for lab. Have a great day.